Everybody? Perfect. Thank you very much. I'm Lucian from University of Lisbon, and I want to present to you C++2Rust, the first automatic translator from C++ to safe Rust. Well, use after freeze and out-of-bounds memory issues. Those are errors you are all familiar with. They are 70% of the security vulnerabilities in software from Google and Microsoft. And we couldn't bring this number down for years. We've tried static analysis, hardenings, fuzzing, code reviews, trainings. None of them worked. In 2019, Google and Microsoft reported for the first time the 70% number. And in 2022, NSA urged people to switch to safe programming languages. While in the following years, the 70% issue still remained a problem. So, our current tools cannot bring down the 70% wall. We need to rethink the memory safety problem from the beginning. So, if our current tools don't work, let's try to switch the language. And this is exactly what happened in the industry, because people started to adopt memory safe languages, which is good, because this eliminates an entire class of memory safety vulnerabilities by construction. However, this is not free. Google, for example, reported that for manually translating WOF2, a font compression library of around 4K lines of code from C++ to Rust, it took 20 days, and in those 20 days, they added 20 bugs that were not present in the original application. So imagine this, 20 days and 20 bugs. We don't want to pay the same price for every rewritten application to save languages. We want to have automatic rewrites that take unsafe programming languages and go automatically to safe programming languages, so that you can push a button and get memory safety for free, without bugs, and instantaneously. And this is exactly what C++2Rust is trying to achieve. Of course, we are not the first to try to solve this problem. C2Rust already exists, and it does a pretty good job at mechanically translating C to unsafe Rust. And it does this because, in general, it's undecidable to statically go from unsafe languages to safe languages due to program properties like pointer aliasing. In this specific example, safe Rust only allows one mutable reference at a time, but our original program contains two mutable aliases at the same time. So because C2Rust cannot fit this, let's say, safe Rust limitation, it chooses to generate unsafe code for the pointer handling parts, which is not ideal because we would like to have 100% safe applications, because even a small, tiny, unsafe block can compromise the security of the entire system. So to solve this problem, we created C++2Rust, which is the first automatic translator from arbitrary C++ to safe Rust. And we managed to generate safe Rust from the beginning because we shift mutability and ownership at runtime. And let me explain you what I mean by that with the following example. So, in the beginning, we wrap all local variables in what we call a value. This value is just a type alias over an RC ref cell of t. And remember the safe Rust limitation that allows only one mutable alias at a time. Well, we would like to have two mutable aliases at a time. And the RC layer allows us exactly this, have multiple layers, and with ref cell mutate through all those aliases at the same time. So because we cannot feed the compile time safe Rust checks, we move the checks at runtime using RC ref cell of t, so that we can handle arbitrary C++ code. Besides this, we create a new type called PTR, pointer, which is just a nice addition over the value model because it keeps a weak reference to an already existing value. And it also supports generic pointer operations, such as taking the address of a value using as pointer and dereferencing the value. And here inside deref is where the interesting things happen. Because on one hand, we need to check that the weak reference still points into a valid value. And on the other hand, we need to check that we can do mutations through the ref cell at that point in time. In this example, both checks pass, so the code is translated perfectly fine. This is the core of C++2Rust, the value and the PTR types. These enable our safe Rust translation. And to better understand the differences between our strategy and the current strategies, take a quick look at this plot. we want to have applications that are both fast and safe. That's our goal. I think we can all agree on that. C++ sits on the horizontal line at the maximum speed. And through the years, people applied mitigations such as hardening, fuzzers, static analysis to make the safety better, right? But this also brings the performance down. So C2Rust come into picture, and well, it generates code which is as fast as the original code, right? Because the code that is generated is unsafe. And through the years, people have tried to make the output of C2Rust safer. But I'm afraid we cannot achieve 100% safety with this, because it's hard to reason about safe properties of the program, like ownership, in the presence of unsafe features like row pointers, for example. So we created C++2Rust, which generates safe Rust code in the beginning. So as you can see, the code is quite slow, because we had a lot of runtime checks to make sure that the properties of the program are still safe. And to fix this problem, we created a set of source-to-source optimizations that bring the performance of the Rust code, of the safe Rust code, as close as possible to C++. We are getting there. I'll present you in a few minutes the optimization that we make, but research is still needed to reach our fast and safe application. Again, C++2Rust, our main bet on C++2Rust is that it's easier to optimize for speed than to optimize for safety. Good. Let's go through a translation walkthrough. We have this beautiful piece of C++ code that we would like to transform to Rust. And I mentioned that we do mechanical translation. So we need a set of translation rules for types and for expressions in general, a function call in this case. And this is the generated Rust code. Don't try to understand it for now, because we will optimize it in a minute. But I wanted to focus on how we got to this code. So our translator is an AST visitor over the Clang infrastructure. So for every type that we visit, we query the translation database and well, emit the corresponding Rust code. And we do exactly the same thing for expressions. In this case, a function call of make unique. And again, this is the generated Rust code. The most important thing about it is that it's safe. It doesn't use any unsafe features. But as you can see, it's not idiomatic. No human being would write this. And it's definitely not fast, because it contains a lot of runtime checks. So to fix those two problems, we created a set of source-to-source optimizations on the generated code. And up until this moment, we are able to eliminate three constructs: RCs, ref cells, and options. And I want to present you what are the, let's say, preconditions for doing each optimization and how the code look at each step. Let's try to eliminate the RCs. The most important precondition for doing this is to make sure that nobody takes the address of the A variable. Remember that in our pointer model, we use a weak reference to an already existing RC. So if we drop the RC, we break the pointer model, which we don't want. But fortunately, in this case, nobody takes the address of A, so it's perfectly fine to eliminate the RC. Good. So the next step is the ref cell elimination. Conceptually, the most important precondition here is to make sure that the ref cell, the dynamic reference, if you want, behave exactly the same as a native Rust reference. And this only happens when borrow and borrow mute are called on this dynamic reference type. Borrow is used for reading, and borrow mute is used for writing. So in this example, only those two methods are used, so it's perfectly fine to do the optimization. We're getting there. The code looks more natural, let's say. And the final optimization is the option optimization. This is quite simple, because in Rust, option is a type that only has two valid states, some and none. And if we only assign some to the option, then the option layer doesn't make sense at all, and we can just eliminate it. And this is the final generated Rust code. It's safe, it's fast, and it's definitely more idiomatic. What you would expect from a good translator. So if you paid attention, I skipped a few optimization passes, because after the option elimination on V, there is still a value, but we rerun the same set of optimizations until we reach a fixed point. And the fixed point is exactly the code below. So saying this, you can think of the middle code, the firstly generated code, as an intermediate representation that we progressively optimize in order to get to the final code. Very well. I hope you got a good understanding of our safe translation with the value in PTR, how we do mechanical translation, and what are the source optimizations. Because I would like to go into some numbers. We managed to translate two security-sensitive applications used in Google Chrome, totaling in 13K lines of code. One of them is WOF2, the font compression library that I mentioned in the beginning, the 20 days and 20 bugs font library. We managed to translate this instantaneously without adding any new bugs. And Brunsley, which is a JPEG repacker. They use a lot of interesting C++ features, a lot of STL, maps, vectors, queues, dequeues, stacks, unique pointers, a lot of those. A lot of OOP with inheritance, composition, pure virtual classes, void pointers for mem copying, mem setting, or just passing generics through functions. And Brunsley especially uses a lot of lambdas to define callbacks that are later passed to functions, or just deduplicate some small pieces of code inside the functions. So for both applications, we compared 3 versions. The original C++ version, the C++2Rust unsafe model. We developed this model only for benchmarking purposes, and the output should be more or less similar to the output of C2Rust. And finally, the C++2Rust safe model, which is the default model, and it's exactly what I presented you earlier with the value pointer and the runtime checks. These are the numbers for WOF2. On the horizontal axis, there are the modes that I told you about earlier: unsafe, safe, safe plus optimizations, the source-to-source optimizations I showed you earlier, and the public data from the manual port. So, and on the vertical axis, there are the metrics relative to C++. And as you can see, for compression time, the numbers are quite flat. And this happens because most of the time is not spent inside our translated code. Instead, it's offloaded into an external crate called Brotli. So the performance impact is not visible at all. But for decompression, the things are a bit different, as you can see. We generate safe Rust code that is 7 times slower than the C++ code in the beginning. And this is exactly the strategy that we choose in the beginning. Generate safe Rust code in the beginning, accept that it's slow, then optimize it for speed. And as you can see, this is exactly what we did. We, using our optimizations, RC, ref, cell, and option, we managed to increase the performance by a factor of 2. The missing optimization here to bring the code as close as possible to C++ would be a PTR elimination well, replace PTRs with native Rust references, mutable and immutable references, because that would clearly make the code faster and more idiomatic. But we are working on this. The memory usage numbers are quite flat as well. For binary size, we also managed to optimize it with our optimizations. And here, for lines of code, it's a bit interesting because Rust is a bit more verbose than C++, especially than the C++ style used at Google. Because, for example, Rust chooses to break each argument on a different line of a function, while the C++ style at Google chooses to fill an entire line with arguments, then break to the other one. Good, so this was WOF2, and this is Brunsley, which is 50 times slower than the original C++ code. And this happens because Brunsley has a different, let's say, profile than WOF2. It uses a lot of pointers to pass data in and out functions instead of returning pointers, and it also has some pointer-heavy loops. And because of that, there are a lot of runtime checks, which bring the performance down. But again, our current optimizer with RC, ref, cell, and option increase the performance by a factor of 8. And again, the missing optimization is the PTR elimination. Memory-wise, we also optimize it because we get rid of RC and ref cells. And the numbers for binary size and lines of code are, again, quite flat. So these two applications, WOF2 and Bruce Lee, we managed to translate them to safe Rust without adding any bugs. And, well, the performance is, we brought the performance as close as possible to C++. And this was C++ to Rust in a nutshell. It generates memory-safe Rust in the beginning, and it optimizes for speed to get as close as possible to C++. The project is open source, so please try it. Thank you.
All right, thanks for the talk. Let's give it to the audience for questions.
So if you take C++ code with some known bugs and issues and run from C++ for your system, which of them are detected on the compile time, which are shifted on runtime, and if they shift to the runtime, how the error handling is implemented, how they're handled?
Yeah, so for well-behaved code in C++, it should have the same behavior in Rust. And for code that has undefined behavior, for example, we translate that to panics at runtime or to compile time errors. Yeah.
So one interesting thing I noticed in your example is that there's a call to a sum function that takes in a pointer, and appears we just kind of believe that that's not doing any criminal activities. Generally, how do you make that assertion, and is it a global compilation argument? And if it's a global compilation argument, how do you reconcile that with the general approach that C++ uses for separate compilation?
I guess you're referring to the example here, right?
Yeah, there's a sum call there, and I just don't believe that I can trust that it was nothing interesting.
Do you mean the sum RC new, refcell new, or?
Line 2.
Sorry.
What's the argument type of sum of the function?
Yeah, so in short, we only do intra-procedural optimizations. We don't look inside other functions. But this is not a fundamental limitation. We can do that, but it's just slower. So
and I think it doesn't take a pointer.
Yeah, sorry for that. It doesn't take a pointer. Yeah, we give up because, again, for the moment, we do intra-procedural, but it's not a fundamental limitation. We can extend that.
One last question.
Yeah, so I have a question about like the design decision, kind of. So from what I understand, we start with like adding these, let's say, boilerplates to the Rust translation, and with the claim that like we need to add this to ensure safety, and we try to remove the boilerplate where we know the code is inherently safe.
Yep.
But I guess like the main problem that we needed C2Rust translation was like the inherent unsafe C++ code, which when you like translate it into Rust still has the boilerplate, and probably that's why you still have like these performance problems, right?
Mm-hmm.
So I want to know like what are the plans for like, because I'm guessing like if somebody did some unsafe stuff in C++, it was because of the performance. And if they want their code translated into Rust, they want those unsafe parts to be taken care of, not the other parts, probably.
Yeah, makes sense. So our source optimization, let's say, feedback, is also designed to be used by humans, not only by a machine to run automatically. So if you have some domain-specific optimizations that you want to do, you can freely do them so that you can recover the optimization, even if the default optimization, let's say, don't know about them. Yeah.
All right, let's thank Lucian again.
Thank you.